Previously, we saw how to describe the elements of a set with roster notation. And roster notation means that we say, hey, the set A is equal to everything that's between these curly braces, and I'm literally just going to write it out, maybe with a dot 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 to indicate that the pattern that I've started keeps on going. So that's roster notation, and this works out okay. But there's a few limitations with it. First of all, we can only write a finite number of elements this way, and even, we don't want to write 100 elements this way. Just three or four is probably about as much as we'd like to do. And second, roster notation doesn't necessarily make it very clear what the pattern is in the elements. If I gave you this set, you would have to make a good mathematical guess and say, oh, this looks like a set with a specific pattern. It's the set of all squares of numbers greater than one. You'd have to kind of intuit that in order to know exactly which set I was talking about. Let's now learn a different way to write sets using what's called set builder notation that allows us to not write out an infinite number or even a large number of set elements, but still allows us to unambiguously describe the pattern. So the way we are going to write set builder notation, I'm going to give an equivalent description of the set A. I'm going to give an example, and then we'll do a formal definition. So just as an example, to get the flavor, I'm going to write x in z, so x in the set of integers, such that x is a perfect square and is greater than 0. So I've used just some English here in the right-hand side to explicitly describe all the possible x's that are going to go in this set. This is an example of a predicate. So the predicate in this expression is this left-hand part here. So this is my predicate that I'll call P of x. A predicate we can think of as a function that accepts an input and returns a logical proposition. Here's an example of a predicate, simpler example. Q of y is the predicate that y is an even number. So y is my input. If I put in a number into my predicate, the result will be a logical proposition. So, for example, Q of 2 is the proposition that 2 is an even number, and that's a true proposition. Q of 3, on the other hand, is the proposition that 3 is an even number, and that's a false proposition. In terms of computer programming, we can think of predicates as closely related to the idea of Boolean functions. So you might have written a Boolean function in an introductory computing class. You might have even written a Boolean function that checks whether a number is even or not and returns true if it is and false if it is not. So predicates are the mathematical equivalent of Boolean functions. So once we have predicates in place, we can use those predicates in order to specify the criteria according to which items are or are not included in a set. So, to finish up our definition of set builder notation, that's the name of this different way of writing sets. Set builder notation. We need two things. In set builder notation, we need a predicate. We just talked about what predicates are. as well as a base set. So the base set says, hey, this is what I'm picking from. I'm going to pick everything in my base set where the predicate is true. This is a little bit mysterious, perhaps, so let's jump right into some examples. I have three sets here, A, B, and C, and I'm going to write each of them in set builder notation. So to do this, I am going to start by asking myself, hey, what's the base set here? Or what am I selecting from? And if you'll notice, in each of these sets, I'm talking about, it looks like positive integers. So we have a special name for the set of non-negative integers. So we're going to use that name here. This is called the set of natural numbers. So n is the set of natural numbers, and it contains 0, 1, 2, 3, and so on. So n is our base set here. We're going to select from among all the natural numbers. And what we need to do is we need to write down a predicate that describes the criteria for inclusion. So here I see that I have numbers 1, 2, and 3 in my set A. So one criteria for inclusion I use, and there might be several reasonable ones, but the one I'll use is that x is greater than or equal to 1, and x is less than or equal to 3. So that's it. I've described my set A in set builder notation. Now, in this case, you might not think that is very rewarding because it took me more writing to write the set builder notation, but soon we'll see some more complicated examples where this does pay off. Let's do another one. Here's B. So B contains the numbers 2, 4, and 6. This time I'll use the same base set. And now I need to figure out a criterion for inclusion. Again, there are multiple reasonable possibilities, but here's one. X is even, and I'm going to say a logical and here. So x needs to be an even number, and x needs to be between 2 and 6. That's one way to describe this set. Finally, let's do one more, set C. So set C here, 1, 2, 3, 5, 7, and so on. This set could be several things, but what I'm intending here is for this set to be the set of all prime numbers, numbers which are divisible only by 1 and by themselves. So here, again, x is in the natural numbers. And here, we don't have any more detailed way to describe this, so we're just going to say x is prime as my predicate. So a few things to notice here. First of all, I can reasonably describe predicates both in kind of English language, like x is prime, as well as in mathematical terminology. It's best to use mathematical terminology when possible, but sometimes we don't always have definitions of these symbols previously introduced, and so we might need to use our words instead. Second, it's okay for a predicate to contain a logical connective or many logical connectives. I can build up predicates out of multiple individual logical propositions in order to construct the predicate that I need. Now that we've introduced set builder notation, which we use to specify sets like A and B, in terms of logical objects, so these predicates, P and Q, now that we've done that, you might suspect, hey, there's some kind of relationship between set theory and logic here. And indeed there is. And let's take a look at how that plays out with with the set operations union, intersection, and set difference that we've seen before. So this requires us to remember some of our definitions. So if we recall, the union is the set of all elements that are in either A or B. And if you're listening for it, you can hear that word or going on. Or describes the union of A and B. And indeed, if A and B are defined using the same base set, which I've done here, they're both defined using the base set S. If A and B are defined using the same base set and predicates P defining A and Q defining B, then it's the case that A union B is the set of all elements of S that satisfy the compound proposition, compound predicate, P of X or Q of X. P of X or Q of X. So if we think of P as the criterion of inclusion for A and Q as the criterion for inclusion of B, then A union B is everything that satisfies either of those two criteria. It satisfies either the criterion for A or the criterion for B. Maybe not surprisingly, if we go on to the intersection, we'll find, hey, in order to qualify to be in the intersection, I need to satisfy the criteria for inclusion for A and the criteria of inclusion for B. So I'm going to write this with an and logical conjunction. In order to be in the intersection of A and B, I need to satisfy P of X and Q of X. Finally, this one is a little bit different. In order to be in the set difference, A set difference B, well here, I need to be an element of A but not an element of B. This means that I need to satisfy P, the criteria of inclusion for A, but not Q, the criteria of inclusion for B. In other words, it needs to be the case that P of X is true and not Q of X is true. P of X is true and not Q of X is true. So when I define my sets using set builder notation, when I perform set operations to combine these sets, the resulting sets can be expressed in terms of logical operators that we know and love applied to predicates. There is another common way to write sets. So far, we've seen set roster notation and set builder notation. I want to describe one more way. Sometimes it's also called set builder notation, but I think that's a little bit confusing. And so I'm going to describe it as set generator notation. Set generator notation. Set generator notation is pretty similar to set builder notation. It has the following form between curly braces f of x, where here f of x is some function. It's a function of x. And then I again have a base set, just like I did in the case of set builder notation. Just now the base set is a little bit in a different place. And I have my predicate. So now I have three elements, and the new one here is this function of x. And this can be any function of x that I want it to be. That's going to be applied to every element of the base set that satisfies the predicate. So let's just go ahead and dive right into some examples of this. So here's a few sets, two sets. And the first one I have written in set generator notation. So what I need to do in order to figure out what this set is first I'm going to look on the right-hand side, right here, first on the right-hand side, And I'm going to figure out what's in this set. Well, it's the set of all integers with the property that x is between 0 and 3. So that's just the set 0, 1, 2, 3. And what I need to do is then apply this function here to each element of that set. So in this case, I have the elements 0, 1, 2, and 3, and I need to apply the squaring function. I need to square them in order to obtain my final answer. So when I square these elements, I get 0, 1, 4, and 9. So this set, 0, 1, 4, 9, is the set described by this instance of set generator notation. Now, I have a different set. It's the set containing the numbers 4, 8, and 12. And what I want to do is I want to describe this set in terms of set generator notation. And sometimes this takes a little bit of ingenuity. What we'll notice here is that these are all multiples of 4, and in particular, it's 4 times 1, 4 times 2, and 4 times 3. So I can write set generator notation here by first, I'm going to start on the right-hand side. I'm going to, again, use integers, and I'm going to specify that the integers are between 1 and 3. So I say I take any integer x with the property that x is between 1 and 3 inclusive, and then the function I'm going to apply is multiplying by 4. So my result is that I've been able to express this set expressed in roster notation in terms of set generator notation instead. I'll just note that there's a useful equivalence between set generator notation and set builder notation. It comes up if I let the function f of x be just x itself, so that's the function where I don't do anything. So this equivalence is that in set generator notation, x, with the property that x is in the base set B and p of x is true, that's exactly the same set, just in different notation, as the set x in B such that p of x. These are the same set, one expressed in generator notation and one expressed in builder notation. You're always allowed to transfer between the two of these whenever you want.